This video will cover model selection and machine learning. By the end of this video, you should understand how to integrate cross-validation and feature selection into a modeling process, and how machine learning concepts can help with the development of forecasting models. As you saw in a previous video, you can use k-fold cross-validation as part of a modeling process to select a modeling specification. You could automate this entire process in an R script. The script could load data, estimate the loss from many candidate models using k-fold cross-validation, choose the best model from this process, then use that model to make forecasts. Whenever you obtain new data, you could just repeat this entire process to update your model. This is actually how forecast modeling is often done. Cross-validation can be used for almost any choice in the modeling process. For example, the features to include in your linear model. You can actually even choose between individual modeling tools. You can also make other modeling decisions. There are often parameters that you need to tune particular modeling tools, and you can actually choose those using cross-validation as well. Just like with feature selection, you're going to iterate through possibilities and choose the model with the lowest estimated out-of-sample fit using your loss function. What that means is the only decision you can't make this way is your choice of the loss function. Remember, your loss function expresses your preferences over different types of errors, and an automated process can't tell you about your preferences. Importantly, this whole process, loading data, cross-validating, feature selection, and forecasting, is a modeling process. Your individual model parameters, specifications, or forecasts may change as you acquire new data and redo this process. More data always means different forecasts. But this process, embodied by the R scripts that you're going to use to implement it, is consistent and well-defined. And an important cornerstone of this is cross-validation. It enables systematic and objective decisions during the modeling process. Computers are really good at these types of problems. So suppose that you have a label that you'd like to be able to forecast. You collect data on past values of the features and labels. You choose a set of possible models that could describe the label. You feed the data and all the possible models into an R script that implements your modeling process. It goes through and it chooses the best model through cross-validation. This is the type of modeling process that we've had in mind, where all of this logic is embedded in R scripts. But suppose instead you have that label that you'd like to forecast. You collected data on the past features and labels. You feed that data into an R script that implements a modeling process. Instead of you providing it with a set of possible models, it knows all the possible models that it could possibly construct given the features and labels. It works through those models, choosing better ones through cross-validation. Along the way, it uses information about which models worked well and which models didn't to try and decide which model to try next. After some period of time of iterating through many models, it finds one that it thinks it works well, and it uses that to generate forecasts. This process that I outlined is the basis of many algorithms in machine learning. It's going to combine modeling tools, evaluation, and other algorithms, and it will use this to determine the relationships between features and labels without any prior knowledge of what the relationship might actually look like. This is very different from how modeling used to be done. Cross-validation is a critical component of this process. It allows you to efficiently compute estimates of the out-of-sample forecast error, so you're able to make choices between the many possible decisions that feed into forecast models while guarding against overfitting.